So now that we have a good understanding of units and the metric system, we can now get a little bit deeper into what we call a derived unit. So as stated in a previous video, a derived unit is simply a combination of SI base units. For example, we looked at the example of combining a length SI unit, which is meter, and a time SI unit, which was second, to get a derived unit that we used for velocity or speed. Velocity isn't the only example. In fact, most units are derived units because they're combinations of those SI base units that we saw previously. Two examples of SI or of derived units that we'll see are volume and density. For example, volume. If you think about what volume actually is, volume is simply a length times a width times a height. It's taking the SI unit of length and simply multiplying it in a factor of 3. Other examples, density. Density, which we'll see in just a moment, is a derived unit where we combine mass and volume. There's some other derived units listed here as well, but the idea is that the derived unit is simply SI units that are combined together. When we think about derived units, we get into the dimensionality of two-dimensional and three-dimensional types of units. So when you're dealing with units that are two-dimensional, such as area, like meters squared, or three-dimensional, such as volume, centimeters cubed, you need to take into account when looking at the numerical equivalence. In other words, when we convert using these two-dimensional or three-dimensional conversions, we have to not only square or cube the unit, but we need to do the same to the numbers. So, for example, let's say we were looking at squaring something. Now, what we should know from the previous video is that 1 meter is equal to 100 centimeters, right? This is a standard metric conversion for one dimensionality. But what if you were looking at meters squared and centimeters squared? If you square the units, you also have to square the number. Where did 10,000 come from? Well, we squared the number 1 and we squared the number 100. Well, 1 squared is still 1, but 100 squared is 10,000. We would do the exact same thing if the units were cubed. So in other words, remember, if you cube or square the units, the numbers also have to be cubed or squared respectively as well. Alright, so let's take a look at an example that'll help illustrate this point. So let's take a look at 24.5 millimeters squared to decimeters squared. So if I write out my starting quantity, okay, ultimately I want to get this from millimeters squared to decimeters squared. Let's ignore for a second that they're even squared. Let's just assume that it was just millimeters converted to decimeters. So what would that look like? Well, I'd do millimeters to meters, okay? And then I would convert from meters to decimeters, because remember, I want to go through the base unit. And so I've got that all set up, so that way my millimeters will cancel, and then my meters will cancel. So decimeters is what I'll end up in. All right, let's just write down what would make these two equivalent to each other. And I'm going to write them to where all my numbers are not written with a negative exponent. And so what I mean by that is, when I'm looking at meters compared to millimeters, the meter is larger, right? So 1 meter, and I'm just going to ask myself, how many millimeters, how many tiny millimeters are in 1 meter? And that's 1,000, right? There's 1,000 millimeters in 1 meter. Notice I'm not squaring anything yet. That's just, in 1 meter, there's 1,000 millimeters. This is the same thing as saying there's 1 times 10 to the negative third meters in 1 millimeter. Likewise over here, the decimeter is smaller than the meter. So in 1 meter, how many decimeters are there? And there's 10. Okay, there's 10 decimeters in 1 meter. Now that's just looking at the numbers in a one-dimensional way. Now, since the units are squared, okay, all these units are squared, I have to also square the numbers in the conversion. So what's 1 squared? Well, it's just 1. But what's 1,000 squared? Well, 1,000 squared would end up being 1,000,000. Okay, I just did 1,000 times 1,000. Over here, I have to square the numbers here as well. 1 squared is still 1, but 10 squared is 100. And so now the conversions are set up correctly because I've squared the units and I've squared the numbers as well. So now the millimeters squared will cancel out there and the meters squared will cancel out there. And I know that these numbers are numerically equivalent. They are now actually correct. And so now I can go ahead and solve. I can do 24.5 times 100 and then divided by 1,000,000. And that ends up getting me my answer, 0.00245, and then the unit of decimeters squared. So that's an example of how you can convert metric conversions using either two-dimensional or three-dimensional numbers. All right, if you're anything like me, visualizing kind of the size of certain measurements is helpful. That way I can understand what units I should be in. So for example, if we're talking about length, okay, the width of a pencil is in the millimeter region, whereas, New York to LA is in kilometers. So it gives you an idea of kind of how big is a meter, how big is a kilometer, how big is a millimeter, things like that. When it comes to volume, a little sip of water is a few milliliters. Whereas if you were talking about a glass of water, that's about 200 to 300 milliliters. A large trash can with wheels is about 400 liters. So these are just giving you visualizations as to how large a unit is. Finally, with mass, just to give you an idea, okay, a nickel coin, about 5 grams. Compare that to a newborn baby, could be about 4 kilograms. Whereas a Honda Civic is 1,250 kilograms. So you can see how they range. I always like to, it's nice to know kind of like how much does an adult weigh, especially when you work in physics. So a lightweight to medium weight adult is about 50 to 100 kilograms. So it just gives you an idea of where everything is relative to one another. All right, we have a few more concepts to cover. Temperature we want to cover real quick in this slide here. So there are 3 temperature scales. There's Kelvin, degrees Celsius, degrees Fahrenheit. First thing I want to point out is notice that for Fahrenheit and Celsius, you have the degree symbol. Kelvin does not have that. Kelvin is just a capital K. But nevertheless, these are 3 temperature scales that you will come into contact with. Fahrenheit's the one that we're used to with everyday temperatures, but Celsius and Kelvin are the temperature scales that we use often in science. Off to the right, it tells you generally what temperature things relatively lie in. Like for example, for body temperature in a Fahrenheit scale is about 96 to 98 degrees Fahrenheit. But you can see how that relates to Celsius. It's between 30 and 40 Celsius, as well as it would be around 310 Kelvin. Absolute zero, which is actually what Kelvin is based off of. You see at 0 Kelvin, this is known as absolute zero. This is where all molecular motion stops. Because remember we talked about earlier in the video series that even solids, the molecules still vibrate in place. At 0 Kelvin, however, which is known as absolute zero, nothing moves. Molecules do not vibrate in place. They actually stop vibrating. And actually 0 Kelvin is theoretically the coldest that you can get. There is some theory that you can actually go colder than that, but we have not at this point reached 0 Kelvin, but we've got pretty darn close. But nevertheless, what we want to figure out is how do you convert from Fahrenheit to Celsius to Kelvin? Well, to get back and forth between Fahrenheit and Celsius, you would want to use these 2 conversions up here. If I gave you Celsius and asked you to convert to Fahrenheit, you would use the first one. Simply plug in Celsius, multiply by 1.8, and then add 32. If I give you Fahrenheit and ask you to give me Celsius, you would plug in Fahrenheit, subtract 32 first, and then divide by 1.8. That would give you your Celsius. But probably the most common conversion that you'll use is how you get back and forth between Kelvin and degrees Celsius. If I give you the degrees Celsius, you would simply add 273.15, and that would give you your Kelvin. And so that's a very easy conversion to use. And like I said, most of the conversions that we'll do in temperature is this last one right here. Because Fahrenheit we don't really use too much in science. All right. The last concept we need to cover in this video is density, and this actually might go on into the next, depending on how long we take. So what is density? Density is a measure of how much matter is compacted into a small spot. So consider these two pictures here. Both squares can be assumed to be the same volume, but you have more matter in this square than in this square. So since there's more matter that's packed away in this volume, this would have a higher density. Whereas there's less matter in this volume, that would be a lower density. You can actually equate this using a mathematical formula, and that is density equal mass over volume. The actual symbol for density is not actually the letter D. It actually is the Greek symbol rho, which looks like a P. So sometimes you might see it written like that. That is the Greek symbol for density. It's not quite the letter P, it looks like it though. And that stands for rho. But either one, you'll see both are used interchangeably a lot. So density can be calculated by taking mass divided by volume. Now, how do you measure density? Well, if density is mass over volume, mass is typically in units of grams, even though kilograms, the SI unit, we'll typically have it in grams. And then volume is usually either in milliliters or centimeters cubed, because remember, they are the same thing. So, units of grams per milliliter or grams per centimeter cubed are used to calculate densities. Liquids typically tend to be grams per milliliter, whereas density of solid objects are grams per centimeter cubed. But remember, since the milliliter and the centimeter cubed are the same, these units of density are the exact same. They can be interchanged. Since gases are very light, you'll see gas densities are in grams per liter. Now, what if I asked you to rewrite this density equation to be equal to mass, right? How would you rearrange this equation to solve for mass instead of solve for density? Well, you would calculate mass by taking density times volume. Now, how did I get that? Well, if your algebra skills are where they need to be at, hopefully you could see how I would have rearranged this equation to solve for mass. But a nice little trick to help you is you can use this triangle down here with density and volume on the bottom and mass on the top. And what you do is you cover the letter that you want to solve for, and what you're left over with is actually the math equation. So for example, if I was wanting to solve for mass, cover mass, what are you left with? Density times volume. What if I asked you to rewrite the density equation in terms of volume? Well, using that same trick, cover volume, what am I left with? Mass divided by density. That's what I would be left with here. So it's a little trick. You can use that to help you solve problems. So on this screen here, we have two problems that will actually compose example 7. All right, the first question says, a sample of pure aluminum has a density of 2.70 grams per milliliter. If a cube of aluminum has a length of 2.0 centimeters on each side, how much mass will it have? So first thing I notice is that it gives me density. Density is 2.70 grams per milliliter, which by the way is the same thing as 2.70 grams per centimeter cubed. It doesn't give me a volume, but I can figure out what volume is because I'm looking at a cube that is 2.0 centimeters on each side. So the volume of a cube is length times width times height. And so 2 times 2 times 2 is 8, and the unit would be centimeters cubed, because centimeter times centimeter times centimeter gives me centimeters cubed. So then, to figure out what the mass would be, I would just take, I would take my density times my volume. So my density is 2.70 grams per centimeter cubed. And I would multiply it by 8.0 centimeters cubed. Notice that when I multiply those, the centimeter cubed will cancel, and I'd be left in grams. So 2.70 times 8.0 gives me a mass of 21.6 grams, or if you've been wondering about sig figs, even though we haven't learned sig figs yet, technically the answer should be 22 grams based on my rounding rules for sig figs. But like I said, I haven't taught sig figs yet. That'll be in the next video. All right. For the last question here, go ahead and pause the video and then hit play to reveal the answer. All right, for the last one, to find the density, we do the mass divided by the volume, which is the difference between these two volumes, to get a density of